Stanford Student Robotics is proud to present our 2020 Rover, Darth Sandious. Iterating from last year's Rover, Anakin Sandwalker, we have created Darth to be sleeker, more robust, and easier to use. Our team of 9 undergraduate engineers has been hard at work creating Stanford's best Rover to date. We believe the key to competition success is extensive testing in pathological conditions and rapid iteration. To encourage this, we have engineered our Rover to facilitate frequent, convenient operation. Darth can be unpacked from a car in minutes and operated without a computer. Camera streams can be viewed on any laptop without external hardware. This allows us to frequently take our Rover for walks and adventures, increasing confidence in our design and our ability to operate it.
Powered by 6 hub motors, our Rover can drive at over 20 kilometers per hour and can run for an hour on a single charge. The e-stop kills power in case of critical malfunctions. Our custom power distribution board prevents issues such as mismatched battery voltages and subsystem level shorts, while watchdog timers gracefully handle gaps in communication. In our modular system, each Linux node is operated independently. Nodes are powered and connected over Ethernet. This makes wiring cleaner and allows development to happen in parallel. We have also continued to develop our custom communication protocol, eliminating lingering issues and expanding support. To facilitate low latency communications over ranges greater than a kilometer, Darth is outfitted with a 2.4 GHz antenna, which, when paired with a directional base station, performs well even without line of sight.
In preparation for the extreme retrieval task, we've made crucial improvements to last year's design. Darth Sandious is equipped with our novel grasshopper suspension, which distributes weight away from the lowest wheel, getting it out of crevices and holes. This system promotes a gliding behavior over both chaotic terrain and large obstacles. We have also worked on improving our Rover's treading, with a focus on the terrain textures present at the MDRS, such as sand, gravel, and stone, without increasing driving vibrations. Our improved camera system allows operators to spot well-hidden objects without sacrificing last year's low latency.
During the autonomy task, the operator utilizes our custom UI to specify multiple waypoints and keep-out zones. Darth's high-precision GPS and IMU are used to follow the path until it reaches the final waypoint and enters search mode. When a competition marker is seen from afar, the Rover approaches to investigate, and once it is certain it has found the correct marker, it will indicate successful leg completion. The autonomy system fuses data from a range of sources to determine if the Rover is stuck and will initiate evasive maneuvers.
Our experience in last year's equipment servicing task demonstrated the importance of being able to precisely and intuitively control the end effector position. We are continuing to use our competition-proven SCARA design and have focused on improving its implementation. Our Z-axis is now driven with the redesigned worm gear system, allowing for increased reliability. We have also improved the precision of our lightweight XY system with the new 2-stage belting reduction on secondary shafts, which lessens gearbox backlash and allows for better belt tensioning without stressing the motors. Low latency camera streams from multiple angles, including a close-up gripper view and a pan tilt overhead, provide the user with several views of the arm. This year's slimmer design allows for easy folding for transport, which facilitates frequent testing. Limit switches on the arm allow it to operate without manual calibration. Additionally, the rumble motor on the joystick provides the operator with force feedback and warns when near inverse kinematic singularities.
This year, our life detection system centers around 3 primary tests: an optical microscope, fluorescence microscopy, and chemical test strips. Our optical microscope is mounted on the chassis of the Rover. Samples are taken and placed on slides, which rotate beneath the microscope. Fluorescence microscopy was the key to our science design last year. We use a fluorophore called separate gold, which binds to nucleic acids and fluoresces only when they are present. Our onboard custom fluorescence microscope can then image the sample, telling us whether or not DNA is present. In addition to standard fluorescence microscopy, we use a lysozyme to break cell membranes. If the amount of fluorescence increases when the lysing agent is added, that means that there were nucleic acids locked inside cells, which is clear evidence for extant life in the sample. We are also experimenting with various chemical test strips. These reveal the presence of organic molecules in the sample, such as lipids or sugars.
For our iterative design philosophy and hard work, we at Stanford Student Robotics have created our best Rover to date. We're confident in Darth's abilities and are excited to compete at URC.